Good morning, class. Now that I have my tablet back, we can continue. We're looking in Chapter 1 at measurements and converting notes. Okay? So, we're going to start with, first let me explain that we are going to have some information here that you're probably familiar with, but there'll probably be some new information too, so it pays to pay attention. All right, so the first thing we're going to do is look at the term measurement, just to make sure everybody understands what that is. We want everyone to start on the same page. So, a measurement is an amount of a quantity indicated by two things, a number and a unit. If it's just a number by itself, it's not a measurement. It has to have a unit of measure. Okay, for example, 10 grams. 8 inches, 25 kilometers, or even 55 pounds. But if it's just a number by itself, it is not a measurement, okay? So now, let's talk about what the unit is. The unit is basically how big the chunks are that you're measuring the quantity with. For example, inches and kilometers both measure distance, but they're different size chunks. Inches are small chunks, so 8 inches is not very big. 25 kilometers are big chunks. They're about 1.6 miles. So 25 kilometers would be a very big distance. So the unit right at the end of the measurement is the size of the chunk that you're measuring with. For example, for distance, we can have other units such as centimeters, feet, or miles. Those are some other distance units. Time. With time, we could have seconds, minutes, hours, days, weeks, months, years. You get the idea, I'm sure. Okay? With mass, we could have chunks of, say, besides grams and pounds, we could have milligrams, we could have tons, we could have kilograms. Okay? So there's all different size chunks of measuring things, but those size chunks are the units. Now, how do we know how big a particular unit is supposed to be? For example, you all have seen yardsticks and meter sticks in school before. How did the factory know how long to cut those sticks in order to sell them to schools for us to use? Somebody somewhere had to make a choice on how big these units were supposed to be, how big the chunks were. That would be the scientific community. They decided how big that each size chunk was supposed to be. And we call the choice that was made the standard. And we're going to take a few minutes here to look at some 3 of the most basic standards. All right, now there's not a lot of room here, so if you want to flip over and write on the back of your paper, obviously you can do that. Just draw an arrow to show that you've flipped over. But the standard is the amount chosen by the scientific community to be the size of a particular unit. Okay? So if we wanted to see how close our meter stick was to the standard, we would have to go compare it to the standard. So let's see what it is. Now, 1 meter actually used to have there used to be other standards for the meter. It's been changed over the years. For example, back in ancient Egypt, they had a measure of distance very similar to a meter. I don't remember the name of it, but it was basically from the tip of a person's nose to the tip of their fingers when they held their arm out to their side. Now, the only problem with that measure is that people have different size arms. So it wasn't much of a standard, was it, if different people's measurements were slightly different. So today, 1 meter is standardized according to an amount that never changes, never. And that would be the speed of light. It's based on that. The speed of light never changes. And oops, there's the first bell. You can tell I'm doing this at school. Just hang on. There we go. Okay, so, and they'll probably do the pledge here in a minute. All right, since the speed of light doesn't change, they decided to base the measure of the meter on that. Now, what would it be? Remember, the speed of light is a speed, so how do we relate it to a distance? Simple. 1 meter is equal to the distance light travels in a given fraction, a given piece of 1 second. Now, what does that mean? Well, if you'll think about it, light to us looks like it's instantaneous. You flip a switch, the light appears instantly. It doesn't seem to take time to go from the light fixture to our eyes. Well, that's only because it's such a short distance. Light travels so fast that it appears to be instantaneous. If we could see light traveling over much, much longer distances, we would see that it does take time. For example, it does take light from the sun 8.3 minutes to reach the earth. So the earth is a long, long way from the sun. Now, a meter is a very short distance. So the light travels very quickly over that very short distance. In fact, it takes a tiny little fraction of a second. Okay, it's way down the decimal line, like 10 or 12 places. Now, do we need to know the given fraction? No, I'm not going to require you to know that. That's something you can look up if you're really that interested. But just know that's an itsy-bitsy fraction of a second. How far the light travels in that time, that's 1 meter. Okay? Now, let's look at a simpler one. Let's look at the kilogram. How do we know how big a kilogram of mass is? Well, somebody in the scientific community said, okay, here's this big chunk of metal. Let's just lop off a bit and call it a kilogram. And you know what? That's exactly what they did. So 1 kilogram standard is a chunk of platinum, iridium alloy. It's just a chunk of metal, an alloy made out of platinum and iridium. Iridium and platinum are both rare earth metals. So they simply took a chunk and said, we're going to let this be a kilogram. Now, how do the factories know? Well, they compare their molds that they're going to use to make their kilograms that they sell to schools, the brass weights and masses that we use in science classes. They compare them to the standard to see if it's the same amount of matter. If it is, those are 1 kilogram masses. The last one we're going to look at is 1 second. All right? Now, a second is defined as a given a given number of vibrations of cesium atoms, ooh, that sounds weird, in an atomic clock. Okay, well, you know how they wanted to base the meter on something that never changes, the speed that light travels? Well, they wanted to do the same thing for the second. Well, cesium atoms are radioactive, so they vibrate at a regular rate all the time. It's extremely rapid, okay? So fast you couldn't see the vibrations. So they simply said, okay, we're going to count off a number of vibrations, and the time it takes for those vibrations, we're going to call a second. Now, cesium atoms today are used in the atomic clocks placed around the world to help keep time. There's one in Boulder, Colorado, and believe it or not, all of your phones are connected via satellite to the atomic clock, which is why your phones all keep correct time. So, do we need to know the number of vibrations that we have to count off? I don't know what that was, but it stopped, so there you go. Anyway, do we have to know the number of given vibrations that it takes to time out a second? No, you could look it up if you're interested. Just Google it. It's a huge number, like 9 kajillion. But that would define what a second is. All right, so in order to know how big units are, we compare them to standards. Somebody chose what size each of these units would be. Now, there's 2 systems of measuring that we have in the United States. Kind of sad because nobody else has 2, everybody else has 1. We'll talk about it. The first is the U.S. customary system. Some of you may call this the English system, but basically it's the U.S. customary system. This is what we use for everyday stuff, okay? Unfortunately, it's not really used by other nations anymore. They've all gone to the other system we're going to talk about. So some examples of U.S. customary units would be pounds, feet, gallons, if we're talking liquids, inches, pints, cups, tablespoons, all of that. Those are all U.S. customary measurements. All right. The other system that everybody else uses is le système international. Oh, there's the late bell. We call it SI for short because here's an S here, here's an I here. So SI for short. So when you hear me say SI, we're talking about this system. This is used by all other countries for everyday measurements. Now, we're about the only country that doesn't use SI exclusively. There may be a few smaller countries scattered around here and there, but very few, if any. We do use SI for science and engineering here in the United States, but for everyday stuff, anything else, we still use U.S. customary. Now, some examples of SI units would be grams, liters, of course, meters, grams, liters, meters, say kilograms, centimeters. All right, measurements like those. A lot of you might call those metric units. Metric is actually an obsolete term now. We use the term SI now, so just keep that in mind. What are some reasons why the U.S. should switch completely to SI? Should we? Shouldn't we? The problem is people don't like to change, okay? Now, in America, because we're a free country, people have made their voices heard and they don't want to change. Other countries, they've pushed it through and they're all on the same system, but we're still using a lot of U.S. customary. You go into the grocery store and you look on the box labels and you will see that there are both U.S. customary and SI units on box labels. Hopefully one of these days we'll get switched over and we're going to look at some of the reasons why we probably should do that. The first reason is that, well, like I said, everybody else uses SI. Okay? We're about the only country that doesn't. Secondly, all right, we already use it. We already use SI for science and engineering, just like other countries. Because if we want our parts and pieces to fit with the ones that we get from, say, China or England or Germany, we want them all to fit together, so we have to use the same SI units for science and engineering that they do. And thirdly, well, it's a system that's actually easier to use because the units are all multiples of 10. They're all multiples of 10. So it's a base 10 system. In other words, for example, there are 10 millimeters in 1 centimeter. There are 10 centimeters in 1 decimeter. There are 10 decimeters in 1 meter. There are 10 meters in 1 decameter. So everything is based on tens. But the U.S. customary system, it's not. So there's a whole lot more you have to remember. For example, if you want to look at distance, there are 12 inches in a foot. Okay, are there 12 feet in a yard? No, you have to learn another number. There's only 3 feet in a yard. And if you want to look at how many yards there are in a mile, well, it's not 10, it's not 100, it's not a multiple of 10. There's about 5,200 and some odd feet in a mile, yards, sorry, it is feet in a mile. So the numbers are all different, and you have to learn each one if you want to be able to convert from one to the other. So it's easier to use SI because everything's multiples of 10, 100, 1,000, much simpler to use. Now, let's look at some of the base units we'll be working with and what their symbols are. Okay, what their unit symbols, that we really should put that right there, unit symbol. All right, so length, the base unit is the meter, and we use an M at the end of the measurement, and you could use it, for example, to measure the length of a table. Okay, mass is measured in a base unit called the kilogram. And yes, it is the kilogram, not the gram, but we'll talk about that later. We use a kg for kilogram at the end of the measurement. An example of where you could use it would be maybe the mass of a cement block. Okay? Time is measured in the seconds. We use an S at the end of the measurement, and maybe you could use a second to measure the time for a sneeze, although it'd probably be a fraction of that, maybe a hundredth of a second for a sneeze. Temperature. Now, a lot of you know that you've heard Celsius and Fahrenheit on the TV, but actually the base unit for temperature in SI is the Kelvin. We use a capital K for Kelvin, and you could, for example, measure the temperature of the sun, or maybe the temperature of an oven. Okay. The last one we're going to look at is electric current. All right, what we use to bring energy to our homes and our electronic gadgets. So it's measured in a unit called the ampere, named for Andre Ampere. Okay, they call them amps for short out in the industry, just amps of current. We use a capital A for amps of current, and it could measure the current in the circuit in your home. Okay? All right, so those are the base units and their unit symbols. Remember, these go at the end of the measurement. Let's do that right here. Written at end of measurement. Remember, all measurements have a number and a unit. So that's the unit symbol that goes at the end of the measurement, so everybody knows what size chunk that measurement was taken in. All right, so now we're going to look at converting between units. And there's two things we're going to look at. First is converting between SI units. That is the prefixes like kilo and centi and micro and nano and mega. Then we're going to look at converting between U.S. customary and SI units. How do we go from the English to the SI or metric units? So let's take a look. First off, you have to understand that every decimal place in SI has a prefix. It has a name. Okay? And we're going to look at the common ones that we use. Now, every one of these decimal places, there's the decimal, every one has its own name. But we don't really use a lot of them. So we're only going to use the most common ones, if that's okay with you guys. All right? So, first off, we need to understand, where would the base unit be? It'd be right here. And this is where, this is the base unit. And this is where you'd have your meters, your grams, yes, your grams this time, seconds and liters, or your amperes, or your Kelvin. Okay, if you have one of anything, that would be 1 meter, 1 gram, 1 second, 1 liter. Now, let's go and look at the metric prefix mega. What is mega? Well, think mega, it means big, doesn't it? So obviously mega is going to be a big amount of these base units. So the symbol for mega is a capital M. You could have a megameter, mega gram, mega second, mega liter. So what decimal place is it though? Well, let's look. We have to go 1, 2, 3, 4, 5, 6. Here we go. A 1 followed by 6 zeros. 1, here's a 1, and 1, 2, 3, 4, 5, 6. Well, you might recognize that number as being 1 million. So a mega, anything, is a million of them. If I had a 2 here, that would be 2 million. If I had a 3, that would be 3 million. Okay? So a mega is a million. All right? Let's see. So 1 million megameters would be 1 million meters. 1 mega million would be 1 million meters. Okay? Let's look at another common one, the kilo. Now here's, you've heard the kilo a lot, kilometers, kilograms. We use a lowercase letter K for kilo, and kilo is 1,000. So a 1 followed by 3 zeros. So 1,000 meters would be 1 kilometer, okay, or 1 kilogram. So let's put 1,000 right here. Okay, in fact, I meant to do this. Let's put the M for mega there and the K for kilo there so that you know. All right, now we're going to go to the other side of the decimal line. These we use are the two most used up here on the top. Let's go to this below. That's where we measure more down here. So we're going to look next at deci. It uses a small d, and deci is located right here. So if you have 1 decimeter, you have 1/10 of a meter. It takes 10 of these to make up those. From one decimal place to the next is only a multiple of 10. So 10 of these makes up these, 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 see? So you can see a million of these makes up one of those, because there's 6 tens right there, 10 times 10 times 10 times 10 times 10 times 10. So you have that many zeros there. The decimeter, however, is a fraction, so it is 1/10, or let me see if I can write. Hang on. Paper keeps shifting. 0.1. Okay, it's a 10th. So here's the deci. All right, the next one is centi. Now, centi should be a clue. Where have you heard the prefix centi before? How about century? Or maybe the American dollar contains a small coin called cents, a cent. All right, well, it takes 100 cents to make up a dollar, and it takes 100 years to make up a century. So anytime you have a centi something, it's 1/100th of a whole. Deci is a tenth of a whole. Century is 1/100th of a whole. Because if you say 1 divided by 100, you get 0.01. Okay? All right. Let's take a look at the next one. Let's look at milli. Now, if you have a millimeter, milligram, millisecond, milliliter, we use the symbol lowercase m. So you'd have mm for millimeter, mg. Notice lowercase for milli, capital for mega. All right? And the decimal place is right here. This is the milli. Now, here's a tenth, 100th. So what would that be? All right? That would be 1,000th. Okay? So that would be 0.001. And if you say 1 divided by 1,000, you get 0.001. So a milli is 1,000th. There are 10 millimeters in a centimeter. But there are 10 times 10 or 100 millimeters in a decimeter. And there's 10 times 10 times 10 millimeters in 1 meter. So 1,000. 10 times 10 times 10 is 1,000. Okay? Let's look at the next one, micro. Okay, now we're going to get real small. But before we show how small we're going to get now, we got a little problem. Okay? Mega, capital M. Milli, small m. Uh-oh, what are we going to do with the micro? We've already used big M and little m. What are we going to use for this? Well, when you run out of English letters in science, they go to the Greek letters. And in the Greek alphabet, the symbol that we would use for M is the Greek letter mu, which looks like a U with a long tail on the front. Okay, it's the Greek mu or mu. Some people call it mu, some people call it mu. Either way, that's it. It looks like a U with a long tail on the front side. Okay? Here's where it's located. 1, 2, 3, 4, 5, 6 places from the decimal. There's the micro prefix. Okay? So if you have a micrometer, to get 6 decimal places, you'd have to divide by 1,000,000. So micro is just the opposite of mega. 6 this way, 6 this way. All right? So you get 0.0000001, 1,000,000th. 1,000,000th of a meter. And the last one we're going to look at is nano. Uses the lowercase n, and it's located right here. 1, 2, 3. 3 more places. There's the nano. And it is 1,000,000,000th. If you say 1 divided by 1,000,000,000, you get a nano. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Oh, I forgot the place holding 0 to show where the decimal is. There we go. All right, so those are the prefixes. Now here's the catch. How are we going to use them? All right, well, I'm going to show you. That's what we're going to look at next. All right, let's take a look at the next page. In order to convert within SI from prefix to prefix, you have to have a conversion factor, also called an equivalency, because it basically shows you how 2 unit prefixes are related to each other. For example, we know from our little chart just a moment ago that 1 centimeter is the same as 0.01 meters. That would be an equivalency. This equals this. It's a conversion factor. We can use it. Another example, 1 kilogram equals 1,000 grams. We could use that. That's an equivalency or conversion factor. So this is what we're going to be using to help us convert from a prefix back to the base. Now, what are we going to do with those? Once you know what conversion factor you're going to use, you have to turn it into a ratio. It's called a conversion ratio. Now, do you all remember what a ratio is from math? A ratio is simply one number over another. Okay? Like 22/7. Okay? That's a ratio. In fact, any of you might know, if any of you recognize that, that's actually where the numerical value of pi for circles comes from. 3.14 blah, 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 blah. That's where it comes from. Okay, that's the diameter divided by the radius. But 20, that's the ratio of diameter divided by radius. And but it's a ratio. It's one number over another number. It's a division. All right, so that's what we're going to do with our conversion factors. We're going to make them into a ratio that we can multiply the given number, the given measure that we're trying to convert. We can multiply it by that ratio to get rid of the undesired unit. So let's look. Convert 25 millimeters to meters. All right, well, the first thing you need to convert 25 millimeters to meters is a conversion factor. Well, we know one. We know that 1 millimeter equals 0.001 meters. 1 millimeter is 1/1000th of a meter. We saw that on the little table a moment ago. You could also write it this way. You could say, 1 meter equals 1,000 millimeters. Same thing, okay? Same thing. It takes 1,000 millimeters to make a whole meter. So 1 single millimeter is 1,000th of the meter. Now, whichever one we choose to use, we're going to multiply it by this, but before we can, we got to make it a ratio. So look at what I'm going to do here. I'm going to choose to use this particular conversion factor right here, just for funsies. All right, so first we take our given measurement, 25 millimeters. Now, remember, anytime you have a whole number, you can make it into a ratio by just putting it over 1, because anything divided by 1 is itself, right? Okay, so now we're going to do this. We're going to multiply by a ratio made from this. But we want to cancel out the millimeters. How do you cancel out something in a ratio? Well, it has to be on the bottom to cancel out. Top and bottom, they cancel. So we're going to take the millimeters here and put it on the bottom. And we're going to put the other half of the conversion factor in the top. Now we've made a conversion ratio. The millimeters, when you multiply across the top and bottom, the millimeters are going to cancel. And you're left with 25 times 0.001 meters, the unit we're ending up with, over 1. So when you say 25 times 0.001 and divide by 1, you get 0.02.